logins to Wakari account. And we had that issue that I talked about before the break, but if anybody missed that, it was these usernames have 2 underscores in between the SciPy2013 double underscore some number. If you went through the create an account process and created one with a single underscore, we want you to use this login. And it's not to keep you from making your own accounts. We would love you to use, whatever nickname you want, SparklePony60, etc. But we have AWS nodes for you to use for IPython, and Amazon was nice enough to donate those to us, and we would love for you to use them so they don't go to waste. They need those on to keep them warm in the server rooms. So please remedy that situation if you created your own account. So I'm logged in under one of these new SciPy2013 anonymous accounts here. And Wakari is supposed to be an integrated analytics environment. So we're trying to provide a web-based environment for you to have everything you need to do your data analysis all here, and to make it easy to collaborate and share with other people. It's part of the Open Science initiative. It's very important to be able to reproduce all these analyses, and this way you can share things without having to worry about libraries and everybody having the same versions of things and dealing with all the nonsense with Pandas versions that we were dealing with earlier. So a brief rundown of how to use Wakari. When you first open it up, you've got this nice welcome to Wakari message, and this is actually an IPython notebook session going on here. And we can create new notebooks, either with this nice blue new notebook button or in the file, new. And the IPython notebook, for those who are unfamiliar, is sort of a cell-based, kind of like Mathematica, boo hiss, Mathematica type thing. We can do our normal Python things, and we do Shift-Enter to execute and move down to the next cell. And it can do really neat things, like you can actually execute things right to the shell and get the output. And there's things called magic functions. So we can do all these things with the IPython notebook. It's very convenient. We can go back, we can edit these things, and re-execute them. So we'll do some of the later examples in Wakari in this. We also, there's some tabs up here. In the terminals tab, which is sort of a permanent tab, it should always be there, you can click on it, and we've got a regular IPython shell here. At least one user noticed that you can't do the plots in the normal IPython shell. If you want to use pyplot, that Pylab inline version, all you have to do is click on the IPython with matplotlib and then open another one of those. And it takes a little bit longer, that's why we don't do it by default. And this way you'll have the plots available to you, so you could do things like that, and they show up. In addition to IPython, we've got just regular shell sessions, and this is where you would do things like git clone https this address, which if you have not done this yet, you should follow along with me and clone this repository right now. Is it too small? Okay, if you can't see those, if you go to View and then Workbench, it should reload. It does not? And then they disappear. Is there a zoom in, zoom out issue? I'm not. I mean, we're both using the same hardware relatively. I mean. So while that's loading up, we've got our little, got our file pane over here, and you can do the normal file things you'd want to do, refresh, take a look at the new things that we just downloaded with Git over here. And a little bit later, we'll want to load up and run some of these notebooks. And through the file pane, we can actually just click on notebooks. So we could go into the SciPy folder, exercises, IP cluster, and load up a notebook straight from there. Great. I think that's the important parts. If you can do a shell and you can get to an IPython notebook, then you're going to be OK for what we need to do. So are there any questions about Wakari at this moment? OK. How long what? The AWS nodes, the extra nodes, are only good till noon or 1 o'clock or sometime. As far as how long the accounts are valid, I'm not sure. We'd have to ask Ben. But Wakari is free. You're welcome to make your own account and use it for free as long as you'd like. Okay. Where is Ben? Where are the presentations? The slides? Oh, the slides. And then, how do I open a PDF? I'm a Linux guy, sorry. They're not the same. Mac's just Unix. Okay. Thanks. Okay, great. So this is the introduction to IP Cluster, sponsored by Amazon Web Services. Oh, this is time. Okay. I'm Clayton Davis. I'm working at Continuum right now. I like to work with scientists on taking their workflows when they get a little bit too big for their britches and taking those to the cloud or to the big metal and university campuses. So IP Cluster is attractive to me because it lets us do that with relatively little effort. And so I'll sort of give you the motivation for what this is about. We'll go through a few examples, and we'll do some, some like real math with like probability distributions and stuff. Some people were asking about that, like when are we gonna get our hands dirty? We'll do it. So this is the unofficial Python slogan, at least how I decide to phrase it. CPUs are cheap, but I'm expensive. Well, I'm a grad student, so I'm actually really cheap. But Travis's time is expensive, so I'm just going to say some things that are true, or at least truthy, so with some type coercion, they're true. Right? So we, being people at a Python conference, prefer an expressive language over raw speed, right? So 95% of the time, or 97% of the time, it's fast enough every time, right? And the old Knuth quote, that premature optimization. But scientific workflows can get big. We baby them, we watch them work on our test sets, and then we see a good result, and then we want to use it on all our data, and they just get big, right? So my expensive time, instead of, I developed this thing really quickly, but now I need to run it on all my data, and now my expensive time is being spent waiting, right? Well, in academia, you can just give that to your grad students, but again, you can't do that at Continuum. So let's replace my waiting time with more cheap CPU time. And by cheap CPU time, I mean we can spin things up on demand. We've got Amazon Web Services, Azure, Heroku. You can spin up additional compute gears or whatever the widgets they call them. I don't know, workers, something. All those are interchangeable, whatever. The university clusters, I mean, those are just free if you're paying tuition or if you know somebody there. Right, but we need, so we've got all of this metal or software on top of metal, but we need a nice way to wrangle the data between nodes. We're in Texas. I'm trying to fit in here. I got here like 2 weeks ago. All right, so we need to herd it between all of these, right? So here's an overview in one picture, right? They say a picture's worth 1,000 words. Well, there's like 8 here, so you can make up the extra 992. But basically, what we want is we've got a central controller that we can connect to with one or more clients. If we're collaborating, it would be multiple clients talking to a single controller. And this single controller is going to dispatch data and code to multiple engines on multiple compute nodes. Obviously, these can all be local if you want to. You can run plenty of engines on a single mini core machine if you want. But they can be on as many different physical boxes as you want. It just doesn't matter. So each thing represented, or each little snaky icon, it surprises me how many people don't realize that that icon is actually two snakes. Like, the language is called Python, like that's two snakes. Each of those Python icons represents a separate IPython kernel running. So we're going to use the clients, connect to the controller, control multiple kernels. Right, so the basic use case for IP cluster specifically, as opposed to other like parallel workflows, is these embarrassingly or pleasingly parallel, if you'd like to be more pleasant about it. And by embarrassingly or pleasingly parallel, I mean there's little or no communication between the jobs. You don't have to worry too much about message passing and things like this. And while that seems limiting, there's a lot of things in science that really fall under this. Parameter scans, you've got some model and you've got a grid of parameters. You need to do some factorial design, full, partial, whatever. You want to scan over that. You've got a bunch of blast queries. If you're doing different blast queries, you can just run them all at the same time, put them all in a big batch. You're going to run them all. They don't need to talk to each other. Genetic algorithms, other things like that are sort of probabilistic methods. These you can run, you can explore these parameter spaces on multiple machines and then mash all of the results together. So these embarrassingly parallel workflows seems limiting, but we use them a lot. Right? We want to be able to really max out some resource on all of the nodes we're going to use. Whether it's CPU or RAM or it's 2013 now, so GPUs, whatever it is, we want to max out something on all of these. And we want to move relatively small amounts of data. When you have large amounts of data that either need to move around or are staying on things, you might lean more towards a MapReduce workflow, which will come later. Yes? Yes, yes. So we don't need those little gear Python guys to be on other machines. You can happily run multiple cores, which is, if you go through this workflow, it's really nice because you can run it on your mini core machine and then with the exact same code, then put it on Amazon later once you max out your double Xeon or whatever. Right, so we need a workflow that moves a relatively small amount of data. If we're going to move lots of data, we have lots of data, we're going to need to use something like MapReduce, which comes later. And again, this seems limiting, but this happens a lot. Sometimes aggregates or subsets are good enough. Maybe we're just looking for the best. We're looking for needles and haystacks, right? And we don't need data about all the hay that we just looked through. Like, all we need is when we find needles, that would be a place where we're moving relatively small amounts of data. Or maybe the data is already on the nodes. Maybe your nodes are on Amazon and you're using EBS or something to spin these up, and they already have the nodes on there. Or maybe these other machines have backup data on there, and you've already got the data there, so you don't need to move around a lot of it. Right? So this is the basic use case for IP cluster, yeah. There is. Let me tell you about it. Continuum, the greatest company ever to write Python, produces a product called Numba Pro. It's available as part of the Accelerate package. If you go to continuum.io and check out Numba Pro, it'll let you put a decorator on a function and then compile that to CUDA. It's not perfect yet, but it works on a surprisingly large amount of code. And Numba will let you put a decorator on a function and compile that with LLVM down to CPU code as well. So it's not just GPU. So, and this, you can definitely use both of those together. You can use Numba and IP cluster together. So that's a good question. So this is my hello world. I'm calling it Parallelo world. All right. So we need to create a client object. Right? It's usually a little bit more involved than this client equals client parentheses call. We'll see in the notebook when we do this what sort of options you need to end up putting there. But we create an object. Then we construct a view of this object, right? And the view, we have to choose between a balanced view, and this is a view that lets you execute commands with built-in load balancing. So when you execute commands, it'll just go to whoever's idle. That's nice for some workflows. Or a direct view, which it just sends it to everybody. And then, especially if you're using sort of a blocking method, it'll wait till it all gets back to you. So which one you use depends on what you're doing, right? Then we define a function. This is a pretty typical one. And we run it remotely. So if you recall, direct was the name of my direct view. And we'll just apply that. And it'll apply that to the nodes. And then this is an asynchronous call. It's not blocking. So we'll need to do a get on that response. And then if we looked at the output, this is what we'd get. Okay? Pretty simple. Okay, so let's try this. Let's see how much load we can put on Wakari. So if we go to our Wakari session, if I can find it. If you have the GitHub repo cloned, you should navigate to it in the file pane. So I cloned it as SciPy2013, the default. And in there, and exercises, and then IPcluster is the IPcluster basics notebook, which is the one I have open. Okay, so this is a slight, just a little bit more than the hello world. There's a link there, a shout out to Ian Stokes' IPcluster notebook. If you're interested in this, he does a lot of really interesting things on there, and it's a really good notebook to copy and paste from and use for references. But for right now, we can try to execute this. Remember, Shift-Enter executes a block and moves on to the next one. And I'm pretty sure we're going to get an error here. Yeah. So a couple things changed from the time I wrote these to the actual getting these Amazon nodes working on Wakari. So we'll have to make a couple little modifications. So if we, this button here inserts a block above the current one. And we just want to get the current directory. So pwd works fine. And we're going to need to grab our home directory. We're going to need the absolute path for this home directory. And if you just copy that, however copying works here. And prefix that JSON file with that. Yes. Then it should work. It'll take a minute, but if we look at this, what we're doing is we're giving it this JSON that is a configuration file. If you were doing this locally and you had a profile set up, it would exist in your .ipython folder in your home directory. This little configuration, but this is a custom one, and each one of these JSON files is custom matched up to your brand new Amazon Web Services nodes. We need to give it the path to an SSH key that the AWS nodes have, and then this packer equals pickle says how these things are going to communicate. Sure. So I prefixed this Wakari SciPy-cluster.json. I prefixed it with the absolute path to my home directory. Yeah. Okay, happy? All right. So you guys probably don't need my help hitting Shift-Enter a bunch of times. But if we do that, we get through the first set, and we see that, indeed, we get what we want. We get these hello worlds back from our nodes. We did it asynchronously. We did it remotely on Amazon. We are officially members of the 21st century now, programming Python asynchronously. That's awesome. But sometimes you don't want or you don't need asynchronous calls, and it's easier for you in your workflow to just keep everything synchronous, to just blast out all of your commands all at once, wait till they all get back, and then do something on it. And if you want to do that, all you do is set this option on the view. Remember, our view is called direct, and we set this option block to be true. And then if we do the same thing, we see that the response object that's getting returned is slightly different. Now that response object is giving me a list of the outputs instead of something that I need to get, and it doesn't have this get method anymore. Oh yeah, that's a good question. Okay. Yeah.
I'm getting an error, no engines registered.
Okay, all right. Let's take a minute. Go ahead and execute that whole notebook if you can, and we'll take a minute and help out people who aren't getting this working to get that working. All right.